Okay, so let's start by going through the exam. I just want to go through all these problems, and I want to point out that, you know, the thought process for all of these problems is the same as homework problems I've assigned, example problems I've done. So you have all the stuff you need to prepare for this stuff. If you would like advice on how to use what you have to get ready for exams, I'd be happy to talk about that. But I just sort of want to go through these problems and try to, bring out the approaches for these as we go. So this is exam 2. And a ball is launched from a height of 2 meters at an angle of 30 degrees above horizontal. So this angle is 30 degrees. And the ball would travel through a path like that. And it asks, how high is the ball at the highest point? So we're trying to figure this out. I'm going to use a coordinate system like this. And my time equals 0 instant is going to be when it's launched. And my time final instant is going to be the instant that it reaches the highest point. And now we can start to think about what variables we know and what we're trying to find. Do we know how long it takes to get to the highest point in time? No. Do we know the acceleration? We do know the acceleration. It's free fall. The initial position, we know that's the coordinates of the object at time 0. So that's the coordinates of the object here. Hold on a sec. My ears. Yeah. So that is going to be 0, 2. Do we know anything about the final position? We're trying to find the highest point. So we're looking for PFY. We don't know anything about PFX. The initial velocity, we're going to use that 30-degree angle. So let's see. We're also given that the speed here is 15 meters per second. So to get this initial velocity, we're going to do 15 times the cosine and sine of 30 degrees. And so that comes out to be 12.99, 7.5. And then we're looking for the highest point. Do we know anything about the final velocity? At the highest point, you always know that the y component of the velocity is 0. So VFY is equal to 0. And so now we're looking for an equation that'll let us calculate PFY y. The one that'll work is 2 times ay times the quantity pfy minus piy is equal to vfy squared minus viy squared. And so you have negative 19.62 times the quantity pfy minus 2 is equal to 0 squared minus 7.5 squared. So I'll rewrite this. Negative 19.62 times the quantity pfy minus 2 is equal to negative 56.25. Divide both sides by negative 19.62. And you get that pfy minus 2 is equal to 2.87. Add 2 to both sides, and pfy is equal to 4.87 meters. Okay, so first we want to calculate the acceleration of this system. What are we going to isolate to calculate that acceleration? Total, yep, everything together. So a free body diagram. And let me go back to that for a second. This is a case where the whole system is going to have the same acceleration. There's no cables or pulleys. And that's why we know that we're going to start this by isolating the whole system together. Okay? Okay, so we have a weight force down of, the total mass is 40 kilograms. 40 times 9.81 is 392.4. Then we have a pushing force up on the wheels. I'll call that N total. Then we have the 40 this way and the 90 this way. That's everything. So now we can go to Newton's second law. We have 40, 0, plus 0, negative 392.4, plus 0, N total, plus negative 90, 0. And that's equal to the mass times the acceleration. Is this thing moving, free to move along the X or Y direction? Yep, X. So this is going to be the mass, 40, times the acceleration, A0. We're just looking for that A. So all we need is the X equation here, and it says 40 minus 90 is equal to 40A. So negative 50 is equal to 40A. Divide both sides by 40, and you get that A is equal to negative 1.25 meters per second squared. And now to get that acceleration vector, now we have this variable. Plug that variable back into our acceleration vector, and you get negative 1.250. So now we can use that in the later parts of this problem. Anyone have any questions about calculating that? Okay, so now that we have the acceleration, we're trying to calculate the force vector on the 15 by the 25. So I'm going to draw a free body diagram of the 15. There's a weight force down of 15 times 9.81. That's 147.15. There's a pushing force from the ground that I'll call N15. The 40 Newton force acts over here. The 90 Newton force doesn't act on this one, it acts on the other one. So the only other contact with this boundary is where the 25 is pushing on this. And so the rule for a pushing force is toward the chosen body, perpendicular to the surface, and I'll call that R. And so now Newton's second law says 40, 0, plus 0, negative 147.15, plus 0, N15, this R is in the negative X direction, so plus negative R, 0. Is equal to the mass times the acceleration of the system that we just calculated, negative 1.250. We're trying to calculate this force. So all we need in order to know that force vector is what that R value is. So all I need is the X equation. That's the only one that has this R in it. And it says 40 minus R is equal to 15 times negative 1.25. So that's negative 18.75. Now solve for R, and you get that R is equal to 58.75 newtons. I asked for it as a force vector, so there are two ways you can represent that. You can show this magnitude and just show me the direction that it's acting, or you can give it as vector components. To give it as vector components, just plug this variable back into that red circled vector. And so the force vector on the 15 by the 25 is negative 58.750. So that's part B. Part C is what's the force vector on the 25 by the 15? Well, this is a Newton's third law pair. It's two things applying a force to each other. And so the force on the 25 by the 15 is just negative 1 times the force on the 15 by the 25. And so that's positive 58.750. Anybody have any questions about that one? Okay, then problem 3. This is one on an incline. So you have an incline of 25 degrees. And at this instant, the thing is sliding up the ramp like this. The mass is 10 kilograms. And the coefficient of friction between the incline and the mass is 0.3. And we're trying to calculate the acceleration vector of this block. And then we're also figuring out whether it's speeding up or slowing down. Once we calculate the acceleration direction, if it's in the same direction as the velocity, it's going to be speeding up. If it's in the opposite direction of the velocity, it's going to be slowing down. Okay, so we're going to use a rotated coordinate system like this. There's a free body diagram of the block. There's a weight acting down of 10 times 9.81. There's a normal force perpendicular to the surface. And then the friction force is opposite the direction that this thing is moving. So the friction force is this way. And that's 0.3 times that normal force N. And since we're using a rotated coordinate system, we have to figure out the components of the weight force. So here's our coordinate system. There's our weight force of 98.1. This angle is 25 degrees. That's the angle of the incline. And so the total angle theta that we want to use is 270 plus 25, so 295. And so the weight force is 98.1 times the cosine of 295, 98.1 times the sine of 295. And so that is positive 41.46 for X and negative 88.91 for Y. Okay, so now we can go to Newton's second law. This is the weight force. So one mistake that I see a lot is people put something like this in, but then they'll also put in 0, negative 98.1. Okay, this is the weight force. That 98.1, the 0, negative 98.1 would be the weight force if we weren't using a rotated coordinate system. So this is 41.46, negative 88.91, plus 0n, plus that friction force is in the positive x direction, so plus 0.3n, 0. And that's equal to the mass of 10 times the acceleration. Is this thing moving along the x-axis or the y-axis? X, so I'm going to write the acceleration as a0. And so I'm going to use the y equation to calculate n. This says negative 88.91 plus n is equal to 0. So n is equal to 88.91 newtons. And then I'm going to plug that into the x equation. So the x equation says 41.46 plus 0.3 times this n that we just calculated. Is equal to 10a. And if you do this algebra, you get that a is equal to positive 6.81 meters per second squared. Okay, so the acceleration vector is, you can plug this value for a into this vector a0. Or in other words, it's accelerating in the positive x direction with a magnitude of 6.81. Okay, is that in the same direction or the opposite direction of the velocity? It's in the opposite direction, so we had a velocity this way, an acceleration this way, and so this is slowing down. And then the last question. We have two masses that are connected by a pulley. We have a rolling cart here with a mass of 3 kilograms. And it's connected to a hanging mass of 2 kilograms. And we want to calculate the acceleration vector of that hanging mass and then the tension in the cable. Okay, do these have the same acceleration? No, they have different. So we use a different approach for this one. For this one, we're going to start out by, we're going to just choose one of those bodies to isolate. And we're going to come up with an equation, and then we're going to go to the other body to isolate. So I'll start with the 3. It doesn't matter which one you choose. So a free body diagram of that 3 kilogram cart. We have a weight force down of 29.43. A pushing force from the ground, and then a pulling force from the cable. So Newton's second law says 0, negative 29.43 plus 0n plus T0 is equal to the mass times the acceleration. This is free to move along the x direction, so the acceleration is a0. All we want is acceleration and cable tension. So there's nothing that we want that's in the y equation, so I'm just going to use the x equation. And it says T is equal to 3a. We can't solve it because there's 2 variables. And so now we'll go on and isolate the other one, and we'll come back to this equation after we're done. So free body diagram of the 2 kilogram mass. We have a weight down of 19.62. And a cable force up of T because it's the same cable. And then we have to think for the acceleration, if the first body moves an inch in its positive direction, which way would the second body go? So if we moved the rolling cart an inch in the positive x direction to the right, would this move up or down? Down. And so that means that we're going to call this acceleration 0, negative a. Okay? So that's the trickiest part of these problems, is figuring out the sign of that second acceleration. So Newton's second law says 0, negative 19.62 plus 0t is equal to the mass times the acceleration, 0, negative a. The x equation clearly doesn't help at all, so we're just going to use the y equation, and that says negative 19.62 plus t is equal to negative 2a. And now the two equations that I have boxes around are a system of two equations for two variables. So I'm going to use this first boxed equation and replace the t in the second boxed equation with 3a. So we get negative 19.62 plus 3a is equal to negative 2a. And so 5a is equal to positive 19.62. And so a is equal to 3.924. Well, we want the acceleration vector of the hanging mass. That's what we were asked for. So we have to plug it into this vector, and don't forget that negative sign. So this says that the acceleration of the hanging mass is 0, negative 3.924. And then we just, now that we have this, we want to calculate t. You can use any equation you want to calculate t. I'm just going to use 3 times a. Our a was 3.924, so t is equal to 3 times 3.924. And so you get 11.77 newtons. Anybody have any questions about any of those problems? The daily assigned problems, the weekly assigned problems, the examples in class, those, you have examples from all of those that show you the steps that you need to follow to do these problems. So, you know, I think if your score wasn't as high as you would like it to be, you just need to spend more time going back over those old problems and reminding yourself how to those steps to follow. I'd be happy to talk to you about it if you want study approaches or, but yes, question.
I think we can go over another question from the daily set.
Yeah, for sure.
Could you go over number 4 from the circular graph method?
Yes. Okay. So you have a 60-gram ball, that's 0.06 kilograms, and it's rolling around the surface. So you can think of this as on like a smooth surface that it's rolling around. And it tells you the length of the string, it tells you the ball's speed. It's uniform circular motion, so that means that there's not going to be any tangential acceleration. Okay, so the first thing it says, this isn't a tetherball problem. What keeps this from being a tetherball problem? Tetherball problems, the only contact with the body is the string. This is in contact with the surface underneath, so this doesn't fit that description. And so that changes the way that we approach this problem. So the first step of a non-tetherball problem is to choose a view where you can see the circular path of the object. So this is the view we're going to take. Like, let's think of from above. So I'm going to choose a coordinate system with x that way and y that way. And it doesn't matter what point on this path you choose, the answers you get are going to be the same. I guess I'll choose this point down here, but any one of these 4 sort of quadrant points would be perfectly good choices. You wouldn't want to choose one that's not at one of those quadrants because then you'd have to use cosine and sine. It would just be a mess. Okay, and it doesn't matter what direction it's moving. It doesn't, I mean, it kind of suggests that that's true because it doesn't tell you which way it's moving. So let's just treat it like the velocity is this way, like it's going around this path counterclockwise. It's not changing speed, so there's no tangential acceleration. The centripetal goes toward the center. So like this. And we can calculate the magnitude of the centripetal acceleration as v squared over r. The speed is 2.5 meters per second, so this is 2.5 squared divided by the string length is 0.3, so that's the radius of the circle. And so the centripetal acceleration magnitude is 20.83 repeating. Now that we have the magnitude of the centripetal acceleration and we've already figured out the direction, we know that the total centripetal acceleration vector that's in the positive y direction, so 0, positive 20.83 repeating. And since there's no tangential acceleration, this is equal to the total acceleration. Okay, so now that we have the acceleration, now we go to the free body diagram and Newton's second law. And here's where something happens that hasn't happened before we started circular motion. In the free body diagram, so here's the ball in the free body diagram. There are two forces that just don't show up in our plane at all. There's a weight force that's going, if we're looking from above, that's going straight into the page. And there's a normal force that's coming straight out of the page towards us. Okay? Since we don't have a way to represent that in this coordinate system, that just doesn't go into our calculations. Sometimes you'll see people represent forces like this with symbols like, so you can think of a symbol like this with a dot in the middle. That represents the point of the arrow coming out towards you. So you could write that, the normal force like that, and then they'll represent a force going into the page with an X, like you're looking at the feathers of an arrow going away, and that's the weight force going away from you. But whether you draw those or not, those don't appear in this coordinate system because you can't represent anything going in that direction with our X and Y coordinate system. And so you have these two things that aren't going to show up. The only other thing you have is the cable force that's going that direction. So you could draw it like this, or you could draw it like this, where you just ignore that stuff that doesn't show up in our coordinate system. But either way, when you go to Newton's second law, the only force in our coordinate system is the t in the positive y direction. So we have 0t is equal to the mass, 0.06 kilograms, times the acceleration, which is 0, positive 20.83. The x equation says 0 equals 0, so that's not helpful. The y equation says t is equal to 1.25 newtons. Okay, so if you have a string that can only withstand a tension of 1 Newton, it'll break. If you have a string that'll withstand 2 newtons of tension, it'll hold up. Yes?
What happens to the string if its tension is 1 and the force acted upon it is also stand up?
Yeah, that's a good question. I mean, I think probably the practical answer is the strings, say if you buy a fishing line or something, and the fishing line is rated for a certain number of pounds, they can't manufacture to perfect tolerance, So you want to just, if you're depending on a string not to break, you just want to get something a little stronger than what your calculations say is going to be required.
What happens if you have a string and you apply the exact amount of force that it's able to withstand? Does it slightly hold up, or does it slightly?
Yeah, right. I guess that just depends on whether that rating means that's what it can withstand, or that's the first thing it can't withstand. I don't know the answer to that. Yeah. Any other questions about this? Any other homework questions anyone wants to see? Okay. All right, well, let's go to the next topic. So remember last time we talked about conservation of linear momentum. Now we're going to get into conservation of mechanical energy. And conservation of mechanical energy is always going to be a way for us to relate an object's location to its speed. And so I'm going to tell you what this law is, and then I'll go back and define some of the things we don't need. But here's kind of the end point of all of this. It's pretty simple to state. So here is what's required for this to hold. If there are no changes in an object's thermal energy, electric energy, magnetic energy, and if the only energy change comes from applying conservative forces then the object's potential energy, U, plus its kinetic energy, T, is a constant. Okay, so U is the potential energy of the object. And T is the kinetic energy of the object. Okay, so it's pretty simple. The way we'll apply this is we'll choose two different instants, and we'll calculate the potential energy and the kinetic energy at each one of these instants. And we know that the sum of those two is going to be the same at each of those two instants. And that'll let us calculate, usually what we're going to calculate is the speed of an object. Sometimes we can calculate something about the location instead if we're given the speed. Okay, so before we can use this, we need to first define a few things. So first, we haven't talked about what kinetic energy is, so we have to define that. Then we'll have to define what's called the work. We'll have to define conservative forces. And then last, potential energy. And once we know what all four of these things mean, then we can use this equation. Okay, so the first one is kinetic energy. So this is an amount of energy that an object has at a single instant. And objects can have lots of different types of energy, so this is only one of those types. But the amount of energy that an object has at a single instant. And if the object, so if the object's mass is m, lowercase m, and the object's speed is capital V, then the object's kinetic energy T is equal to 1/2 times the mass times the speed squared. One thing to notice is, so this involves an object's speed, not its velocity. We don't care about the direction, okay? So if the object is going 20 meters per second north, it has the same energy as if it's going 20 meters per second west, okay? But you can calculate this if you have the velocity. So if you know the object's velocity components, the kinetic energy is equal to 1/2 times the mass times the quantity x component squared plus y component squared. So that's an easy calculation, whether you have the speed or the velocity components. The units are the same as every type of energy. And there's a few different ways to calculate this. You can do it as units of force times units of length. But you can, with exactly the same meaning, calculate this as units of mass times units of length divided by, length squared divided by units of time squared. Those don't look the same, but they mean the same thing. And so the SI units are kilogram, let me put it in the same order as before, sorry. So let's say newtons times meters. So that's force times length in SI units. You can also write it as kilograms meters squared per second squared. And since we're going to use units of energy a lot, we give it its own name, the joule. And it's abbreviated with a capital J. Okay, intuitively, this is kind of the way to think about what kinetic energy is, intuitively. As the speed increases, an object's kinetic energy goes up. And the meaning of kinetic energy can kind of roughly tell you so the kinetic energy roughly tells you how much it would hurt if the object hit you. Okay, so if a small light object, a ping pong ball, hits you at 1 meter per second, that's a small mass, a pretty small speed. The kinetic energy is small and it wouldn't hurt very much. If a bus hits you, well, that actually probably wouldn't hurt very much either, but for the instant before you were flattened, it would hurt because a bus has a big mass and it's moving with a big speed, and those together give you a big kinetic energy. Okay. So let's do an example calculation. So let's say a car has a mass of 1,000 kilograms and a speed of 30 meters per second. What's its kinetic energy? The kinetic energy is 1/2 times the mass of 1,000 kilograms times the speed squared, 30 meters per second squared. And so 30 squared is 900. Half of that is 450 times 1,000 is 450,000 joules of kinetic energy. Okay, so let's say somebody asked you whether you want to get run into by this car or a turtle. Okay, so we're going to just to be on the safe side, we're going to do this calculation before we make our decision. So let's say for a second example, a turtle has a mass of 0.1 kilograms and a speed of 0.5 meters per second. That's a fast turtle, actually. And we want to calculate its kinetic energy. So kinetic energy is equal to 1/2 times the mass times the speed squared. And so that's 0.25, 0.125. So this comes out to be 0.0125 joules. And so now you look at your two rough calculations and you say, I'd rather get run into by the turtle, please. Any questions about that? Okay, the next calculation, the next definition we need is work. Okay, so this is important. Kinetic energy, so remember that kinetic energy is an amount of energy that an object has. Kinetic energy is an amount of energy an object has. Work is not an amount of energy an object has. Work is a change in an object's energy that's caused by the application of a force. Okay, so now we're going to think a little bit about how it is that applying a force to an object can change its energy. Well, just loosely speaking, we know that applying a force to an object can make it accelerate, and accelerating can change its speed, and kinetic energy depends on the speed. So you can kind of see how there could be a connection between applying a force to an object and how its energy changes. So if an object's displacement from instant 1 to instant 2 is the vector d. Okay, so this d is the displacement vector of the object from this one instant to this later instant. And the force F is applied to the object during that time interval. Then the work done by that force is equal to the x component of the force times the x component of the displacement plus the y component of the force times the y component of the displacement. And this, by the way, is a calculation called the dot product, and it's written as F dot D. So that's a vector calculation that, but this is how you do a dot product. Okay, so let's do a quick calculation. So let's say if a 3 kilogram object drops from a height of 5 meters to a height of 2 meters, what's the work done by gravity? Okay, so we're going to calculate how much gravity changes that object's energy during that time interval. Okay. Well, the displacement vector is the later position minus the earlier position. So I'll write this as the later position is 0, 2. The earlier position is 0, 5. So our displacement vector is 0, -3 meters. Are you with me on that? And then what about the gravitational force? That gravitational force is mg in the negative y direction. So that's 0, -29.43. And so the work done by gravity is 0 times 0 plus -3 times -29.43. And so the work is equal to let's see, what's that? 3, 9. And so the work is equal to positive 88.29 joules. And the fact that it's positive means that this force increased the object's energy. Okay. Well, does it make intuitive sense that as this object falls, gravity is increasing its energy? Yeah, it's getting faster as it falls. And so you can imagine that the way this would work if the object was moving up is that gravity would be removing energy from it because the object would be slowing down as it rises. Okay. So intuitively, so here's the intuitive result. So first, if the force is within 90 degrees of the displacement vector, then W is positive, and the force increases the object's energy. The within 90 degrees thing just means they don't have to be the exact same direction, as long as they're roughly in the same direction, as long as they're closer to being in the same direction than they are the opposite direction, then that force is going to increase the energy. Okay? So like, for example, I can speed this up by applying a force, like think of the force direction as along my finger. Ooh, that's a lot of friction. Okay, so I'm not applying a force that's exactly in the direction it's moving, but it's more or less in the direction of motion, and so I'm increasing its speed, increasing its energy, okay? On the other hand, if the force is greater than 90 degrees, from the displacement vector, then W is negative, and the force decreases the object's energy. Okay, so that would be like if something's rolling towards you, you apply a force in the opposite direction to it, and that has the effect of slowing it down. Okay, so that would be decreasing the object's energy. Well, what would you guess happens? So the third and last one is, what would you guess happens if you apply a force that's exactly perpendicular to the displacement vector? It doesn't have any effect on the speed, and so the work is equal to 0. Okay, and it doesn't change the object's energy. So if the force vector and the displacement vector are perpendicular, then no matter how big that force is, the work is equal to 0, and the object's energy doesn't change. Isn't changed by the force. Okay? Anybody have any questions about those? All right, so I'll start next time with a little kind of intuitive example of this, and then we'll just keep working towards conservation of mechanical energy. That's all.